Hey everyone! Have you ever heard the word calculus and felt a little shiver of fear? Maybe it sounds super complicated, like something only rocket scientists use. Well, I'm here to tell you a secret. Calculus is actually incredibly cool, and it's all about understanding change and how things move and grow. It's like having a superpower that lets you see the hidden patterns in the world around you. We're going to explore its main ideas together, and I promise, it's way more fun and easier than you might think. So get ready to unlock some amazing math magic with me. The big stars of the calculus show are three amazing concepts: limits, derivatives, and integrals. These might sound like fancy grown-up words right now, but trust me, they are the keys to understanding so many things. Limits help us see what happens when we get super close to a value. Derivatives tell us how fast things are changing at any single moment. And integrals, they help us add up lots of tiny pieces to find a whole amount. Together, these three ideas form a powerful toolkit for solving all sorts of interesting problems, making sense of motion, growth, and so much more. You might be wondering, okay, Danica, but where would I ever this stuff? The answer is everywhere. Seriously, engineers use calculus to design amazing bridges, super fast cars, and even the phone you might be holding. Doctors use it to understand how medicines work in our bodies. Economists use it to predict market trends. Animators even use principles of calculus to make characters in movies move realistically. It helps us understand nature, from the way a flower blooms to the orbits of planets. It's not just for textbooks, it's for real life. So take a deep breath. We're going to break down each of these big ideas: limits, derivatives, and integrals, one step at a time. We'll use simple examples, fun stories, and maybe even a cookie or two, in our imagination at least. My goal is to show you that calculus isn't scary. It's fascinating and full of aha moments. By the end, you'll see how these concepts are all connected and why they are so incredibly important. Let's get started on this awesome math adventure, and you'll see that you totally do this. Let's start with the very first building block of calculus, the limit. Imagine you're trying to get incredibly close to a target, but maybe you can't land on it for some reason. A limit describes what value you're getting closer and closer to as your input or your position approaches a certain point. It's like asking, if I keep moving towards this spot, where will I eventually end up? Or what value will I be aiming for? It's less about being the point and more about the journey, the point from both sides. The cool thing about limits is that sometimes the value of function is more important than the value the exact point. Think of it like zooming in on a map. As you zoom closer and closer to a specific landmark, you get a better and better idea of its precise location, even if you can't physically stand on the exact pinpoint shown on the digital screen. Limits help us understand behavior in these infinitely close situations, which is super important for the other parts of calculus we'll explore later. It's about the trend, the destination that everything points to. So how do we think about finding a limit step by step? First, you pick a specific value you want your input, let's call it x, to approach. Then, you look at what happens to the output of your function, let's call it y, as x gets super close to that chosen value from the left side, values slightly smaller. Next, you do the same thing from the right side, values slightly larger. If the y values from both sides are heading towards the same single number, then bingo! That number is the limit. It's like two friends walking towards each other and meeting at an agreed spot. Why do we care so much about these limits? Because they are the absolute foundation upon which derivatives and integrals are built. You can't truly understand how to find the instantaneous speed of a car, that's a derivative, or the total area of a complex shape, that's an integral, without first grasping this idea of getting infinitely close to something. Limits allow us to work with concepts that involve infinity or infinitesimally small changes, making them the bedrock of calculus. They are the secret ingredient that makes all the other cool calculus tricks possible, believe it or not. Okay, let's make limits even clearer with a fun and rather delicious example. Imagine you have a cookie jar that's full of your favorite cookies. Let's say you decide on a rule. Each time you go to the jar, you take exactly half of the cookies that are currently in there. So the first time you take half the cookies. Now the jar is half full. The next time you take half of so you take a quarter of the original amount. Now you've taken half plus a quarter. You're getting more cookies, but the amount you take each time gets smaller. Let's follow this cookie-eating adventure a bit further. On your first visit, you take 1/2 of the cookies. On your second visit, you take half of the remaining 1/2, which is 1/4 of the original total. So now you've eaten 1/2 plus 1/4, which is 3/4 of the cookies. On your third visit, you take half of the remaining 1/4, which is 1/8 of the original. Now you've eaten 1/2 plus 1/4 plus 1/8, which is 7/8 of the cookies. You can see a pattern here, right? Each time you visit, you get more cookies, and the total amount you've eaten gets closer and closer to the original number of cookies in the jar. The fraction of cookies you've eaten keeps growing. 1/2, then 3/4, then 7/8, then 15/16, and so on. Even though you're always leaving some tiny fraction behind because you only take half of what's, the total amount of cookies you is approaching the entire contents of the jar. In this example, the amount of cookies you can eat as you make more and more visits is one whole cookie jar. You get infinitely close to eating all of them. The key idea here is approaching. You might never eat the very, very last crumb if you could divide it infinitely, but the total amount you've consumed gets so incredibly close to one full jar that for all practical purposes, you've eaten the whole jar. This is the essence of a limit, the value that a process or a function heads towards as something, like the number of your visits to the cookie jar, increases or approaches a certain point. It's about that ultimate destination value, even if the journey involves an infinite number of tiny steps. Limits aren't just for cookie jars or abstract math problems, they pop up in our everyday lives more often than you might realize. Think about driving a car. When you see a speed limit sign, say for 30 miles per hour, you adjust your speed. As you get closer to the zone where that speed limit applies, your car's speed 30 miles per hour. You might not hit it exactly the instant you see the sign, but your speed is trending towards that value. That desired speed is like a limit your driving is aiming for. Consider something from the world of technology, like a video game. Imagine your character is running towards a solid wall. In some game physics, your character might get incredibly, infinitesimally close to the wall, but never pass through it. The distance between your character and the wall approaches zero. Zero, in this case, is the limit of that distance. It's a concept that helps define boundaries and interactions in virtual worlds, making them behave in predictable ways. How about when you're baking a cake or some delicious cookies? You preheat your oven to, say, 350 degrees Fahrenheit. The oven doesn't instantly jump to 350 degrees. Instead, its internal temperature gradually increases, getting closer and closer to 350 degrees. It might even fluctuate slightly above and below that temperature as the thermostat works to maintain it. That target temperature of 350 degrees acts as a limit which the oven's actual temperature is constantly trying to approach. This ensures your treats bake perfectly. Even in nature and medicine, limits are at play. When a doctor prescribes a medication, they consider how the concentration of the drug in your bloodstream will change over time. After you take a pill, the drug level might rise, peak, and then gradually decrease as your body processes it. The concentration might approach zero over many hours. Understanding these limits helps doctors determine correct dosages and timing for medications to be effective and safe. It's all about how quantities approach certain values over time. Now that we've got a handle on limits, let's jump into the super exciting world of derivatives. If limits are about approaching a value, derivatives are all about how fast things are changing at one specific, tiny instant in time. Imagine you're on a thrilling roller coaster. At some points you're going super fast, at others you're slowing down. A derivative would tell you your exact speed at any single moment on that ride, not just your average speed over the whole trip. It's like a super precise speedometer for any changing quantity. Think about it this way, your car's speedometer shows your speed right now. That's a perfect example of a derivative in action. It's telling you the instantaneous rate of change of your car's position. If your position is changing quickly, your speed is high. If your position is changing slowly, your speed is low. Derivatives help us quantify this rate of change for all sorts of things, not just cars. It could be the rate at which a plant is growing or how quickly the temperature is rising on a summer day. So, how do we find this magical, instantaneous rate of change? This is where limits come back into play. If you have a graph that shows something changing over time, like distance traveled versus time, the derivative at a particular point is the slope of the line that just barely touches the graph at that single point. This line is called a tangent line. To find this slope, we use limits to look at the slope of lines between 2 points on the curve that are incredibly close together, and then we see what happens as those 2 points merge into one. But derivatives aren't just about physical speed. They can describe any rate of change. For example, if a company is looking at its profits over time, the derivative would tell them how quickly their profits are increasing or decreasing at a specific moment. This is called marginal profit. If a scientist is studying a chemical reaction, the derivative can describe how fast the concentration of a substance is changing. It's a super versatile tool for understanding the dynamics of almost anything that doesn't stay still. Let's dive deeper into where we see derivatives making a difference. Think about those amazing, twisty roller coasters again. Engineers who design these incredible rides use derivatives constantly. They need to know the exact velocity, that's speed and direction, and acceleration, which is how quickly velocity is changing, at every single point on the track. This ensures the ride is not only thrilling but also completely safe for everyone. The steepness of a drop or the sharpness of a curve are all related to derivatives, helping calculate the forces you feel. Consider your morning cup of coffee or tea. When you pour a hot drink, it starts to cool down. The rate at which its temperature decreases is a derivative. Initially, when the drink is very hot and the room is much cooler, it loses heat more quickly. The derivative, or rate of cooling, is larger. As the drink's temperature gets closer to room temperature, it cools down more slowly. The derivative becomes smaller. This is an example of Newton's law of cooling, which involves derivatives to describe the process. This picture shows exactly what we mean by a derivative visually. That straight line, the tangent, just kisses the curve at one spot. The steepness of that tangent line tells you how fast the quantity represented by the curve is changing right at that exact point. If the line is very steep, the change is rapid. If the line is flat, there's no change at that instant. It's a beautiful way to see instantaneous change in action. And it's not just about physics or engineering. In economics, businesses use derivatives to make important decisions. For example, they might want to find out how much their production costs will increase if they decide to make just one more item. This is called marginal cost, and it's calculated using a derivative. Knowing this helps them optimize their production levels to maximize profit. So, from the thrill of a ride to the strategy of a business, derivatives are quietly working behind the scenes, helping us understand and shape our world. All right, we've explored limits, getting close, and derivatives, how fast things change. Now let's meet the third member of our calculus dream team, integrals. If you think of derivatives as breaking things down to look at instantaneous rates, then integrals are kind of the opposite. Integrals are all about putting things back together, summing up lots and lots of tiny little pieces to find a total amount or a whole quantity. They are the ultimate adders in the world of calculus, helping us find accumulation. Imagine you have a really weird curvy shape like a blob, and you want to find its area. You can't just use a simple formula like length times width because the sides aren't straight. This is where integrals come to the rescue. The brilliant idea behind integrals is to slice that weird shape into a huge number of super thin rectangular strips. Each strip is so thin that its top edge is almost flat. You can easily find the area of each tiny rectangle, and then you add up the areas of all those tiny rectangles to get the total area of your blob. Integrals do this summing process perfectly, as if you were using an infinite number of infinitesimally thin strips. This means you get the exact area, not just an approximation. The symbol for an integral even looks a bit like a stretched out S, which stands for sum. So whenever you see that symbol, think summing up tiny bits. It's a powerful way to handle quantities that are accumulating or to find areas and volumes of complex shapes that regular geometry can't easily manage. The step-by-step idea is often described as finding the area under a curve. If you have a graph, and the curve on that graph represents something, like your speed over a period of time, or the rate at which water is flowing into a tank, the integral can help you find the total amount accumulated. For instance, if the curve is your speed, the area under that curve will give you the total distance you've traveled. It's like adding up all the tiny distances covered in tiny moments of time. Integrals are incredibly useful for finding all sorts of totals in real life. Let's say you're driving a car and your speed isn't constant. Sometimes you speed up, sometimes you slow down. If you have a graph of your speed over time, an integral can calculate the exact total distance you've traveled during your trip. It does this by adding up all the tiny bits of distance covered during each tiny moment of time, even when your speed is changing. It's much more accurate than just multiplying an average speed by time if your speed varies a lot. Think about filling a swimming pool, or even just a bathtub with water. What if the rate at which water flows from the hose changes over time? Maybe the water pressure fluctuates. An integral can help you figure out the total amount of water in the pool or tub after a certain period. It sums up all the little bits of water that flowed in during each tiny interval of time, even if the flow rate wasn't steady. This is super helpful for engineers designing reservoirs or managing water resources. This visual shows the core idea of an integral beautifully. The shaded region represents the area under the curve. If that curve represents, for example, the rate at which you're earning money per hour, and maybe that rate changes, then the total shaded area would represent your total earnings over that period. It's a fantastic way to visualize how these accumulated totals are calculated from rates that might not be constant. Integrals also show up in places like calculating how much paint you need to cover a curvy surface, or in medicine to determine the total exposure to a drug in the body over time. Even in computer graphics, integrals are used to calculate how light interacts with surfaces to create realistic images. They help figure out the total effect of many small contributions. From calculating the work done by a force to understanding population growth, integrals are the go-to tool for summing things up in a dynamic world. So we've journeyed through limits, derivatives, and integrals. Let's take a moment to see how these three amazing concepts are all connected, like best friends working together on a super cool project. First up, we have limits. Remember, limits are the absolute foundation. They help us understand what happens when we get infinitely close to a value or when we're dealing with infinitely small pieces. Without limits, the precision needed for derivatives and integrals just wouldn't be possible. They set the stage for all the calculus magic. Next, we have derivatives, which are built directly upon the idea of limits. To find an instantaneous rate of change, like the speed of a car at a specific moment or the slope of a curve at a single point, we use limits. We look at the change over tinier and tinier intervals, and the limit of these changes gives us the derivative. So derivatives tell us how fast something is happening, and they rely on limits to give us that at this very instant precision. They are all about analyzing change. Then come integrals, which are often seen as the reverse process of derivatives. If a derivative breaks something down into its rate of change, an integral sums up those rates of change to give you back the total. For example, if you know your speed, a derivative of distance, an integral can tell you the total distance traveled. Integrals also use the concept of limits when they sum up an infinite number of infinitesimally small pieces to find a total area or volume. So they answer how much has accumulated, using limits in their summation process. Together, limits, derivatives, and integrals form the core of calculus, known as the fundamental theorem of calculus, which explicitly links derivatives and integrals. This powerful trio gives us the tools to model, understand, and predict the behavior of systems that are constantly changing. From rocket science and engineering to medicine, economics, and even understanding the natural world, these concepts are essential. They allow us to move beyond static problems and tackle the dynamics of real life. So calculus isn't just math, it's a way of thinking and seeing the amazing, ever-changing world around us.